Okay, so thank you for the introduction, Alistair. So I'm going to just launch straight into it so that we try to keep a little bit on time. So what I'm going to do today is I'm going to talk a little bit about energy meteorology, so what my group does, and talk a little bit about past, so looking at what we can learn from our past data, and then looking at what we can actually learn from the future. So this, I think, nicely follows on from what Muriel was talking about in terms of climate change. So what I'm going to talk about today is how the impacts of climate change may affect where we choose our solar and our wind sites in the future. A little bit about what I do and what my group does. What we try to do is look at the interactions between the weather and climate and the meteorology and how that impacts different types of energy technologies. And we want to be able to develop models that lead to, cost-effective and sustainable management strategies. So in terms of what we can do with energy meteorology, we can do resource assessment, looking at siting and planning, forecasting and optimization. So weather forecasting is one of my things that I'm really passionate about working on. It can also assist in technology design and building optimization. So in terms of the ongoing projects that my group works on at UNSW, and some of this work is with Alistair, in terms of looking at weather models for building energy management optimization. So the weather essentially is what we're interested in and how it impacts different technologies. So whether it's the building or whether it's solar, whether it's wind, even hydro when we're thinking about climate, wind forecasting and assessment, hybrid forecasting and optimization of battery storage, so looking at hybrid plants that are composed of PV and wind and how battery storage can be used to assist in enhancing the output from those farms. Distributed forecasting, so something that we have a student who works with solar analytics is working on, and aerosol modelling and forecasting for concentrated technologies. So this is quite close to my heart because this goes back too many years to count now when I did my PhD, which was on aerosol modelling. And I know we're in a lecture theatre, so I feel like an end-of-year lecture almost, and I'm going to ask you a question as well. Who can remember in 2009 the severe dust storm we had where everything was covered in a red haze? It was absolutely horrible, wasn't it? And not just for having to clean all that red haze and dust up, which lingered in the air for so long, but also if you were in the energy industry, thinking about the effects that would have had on your PV panels or your concentrated solar technologies. So there's that side as well. So what I'm really interested in is having a look at different types of aerosol models, how they impact these technologies. So you can get about a 30% reduction in irradiance by dust particulates and aerosols if it's around where a concentrated solar technology is located. And you can see from our little map here, most of that originated from the Strzelecki Desert. And this also comes about with thinking about weather and climate. So it was in 2009 and it was an incredibly dry period. We were suffering a drought. And all this dust was carried along by intense frontal system. And we can see how far that dust actually carried. So it originated in the centre of the desert and as far reaching as New Zealand actually saw the impacts of that dust storm. So what I'm going to do is talk a little bit about characterising our data. So this is looking to the past and historical data to see what we can learn from that. And then I'm also really interested in extreme events and how often they occur. And then what can we learn about the future? And that's where we run our climate models. So what I'm interested in doing is identifying weather patterns that also correlate to periods of high and low power production. And we're looking at DNI for the moment. So this is satellite data that we've had a look at. And we wanted to know, so over Australia for the past, say, 20 years, what were the consecutive number of days where we would see no irradiance at a particular location? And I'm sure there's some developers and people in the industry out there. And you think, well, if I'm siting or choosing a location for, say, a solar site, I want to know how much am I going to be earning from that site? How many downtime days am I going to have from that location, and how my technology is going to operate in that type of weather and those type of climate conditions. So what we have a look here is our consecutive number of days, and we can see at the top part of Australia, so kind of our Queensland area here, our data said that the longest number of days we actually saw was around 20 consecutive days without any irradiance. And now I'm interested in the weather, so then I think, well, what could have caused that? And we have a look at our map here, which tells us when are we likely to see these lulls occurring. So we can see in our summer months, our January, December, the top of the continent is when we're going to be more likely to see those lulls. And in the southern part of the continent, it's our winter months. So can anyone think of something that might be causing, and I knew Alistair was going to put his hand up, that might actually cause those lulls?
A whopping big cyclone.
Maybe. Close. We will talk about cyclones later on today, but the monsoonal trough. So the rainy season that we see at the top of our continent, which occurs between roughly November to February. So it's this large trough that kind of moves up and down at different times of the year. And in summer is when we have the rainy season across that part of the continent. And it actually can cause lulls of around 20 days as an extreme. So that's a huge impact if you've got a technology there. And then going back to our dust storm event, which I find very interesting, we then had a look at, well, if we were just looking at that particular day, what does our irradiance map look like? And you can see that this is Cobar, and Strzelecki Desert kind of was around here, but you can see how most of New South Wales has irradiance values less than around 150 watts per metre squared. Incredibly low, and that lasted for an incredibly long period of time as well. So that's looking to the past. And we can get a lot of information about the past. Continuing on with our past, what we're also interested in looking at is, so starting to think about changes in climate. If we look at the last 20 years or so of data, what can we infer from how the climate is changing? So we're looking at our changes in DNI again, and we've broken up into season. So what we've looked at is how far has the irradiance deviated from the average? Are we seeing overall a loss or a gain over this 20-year period? So interestingly enough, we have a look at summer here. We're actually seeing a loss has been occurring over the last 20 years. So we're seeing less irradiance values in the top part of the continent. So, you know, there's a few things we can infer from that. Are we starting to see more rainy periods where our irradiance values are lower? Are we seeing more cloud cover? And these are some of the things that we investigate. In terms of some of our other seasons, we can see that in the southern part of our continent, we're actually starting to see a gain in our irradiance data. So this is DNI, by the way. And some of our investigations are looking into why are we seeing these changes? Is it impacts of aerosols or is it impacts of clouds? So now this leads me on to how changes in climate can actually impact the way we think about siting of either solar or wind. So I'm actually going to be talking about wind today, because the way this all came about is Jason Evans, so I'm working with some great people in the Climate Change Centre, but Jason Evans gives a guest lecture for my first year course on sustainable energy. And of course, you know, you have a little chat about what you're doing and how research is going. And he was telling me about some of the models that he was running, and I was telling him about some of my wind energy work. And we were thinking about, well, when you're thinking about siting a wind farm, you either put up met masts for a period of time, or you look at kind of historical data to get an idea of, well, what's the resource going to be like? But then you think about, well, I'm investing in a wind farm and it's going to be lasting for, say, 20 to 25 years. That's looking into the future. So if I'm using data to tell me how much I'm going to be getting into the future, am I going to be getting a really good estimate of the financial viability of this site, or should I be starting to look at climate models and see what information we can get from those? And that's essentially what we've done. We've had a look at some of the climate models to work out, well, are these locations where wind farms are already located going to be economically viable in the future? So if a wind farm's had its lifetime and they want to put new turbines on the site to continue it operating, is that worthwhile? Or should we be looking at other sites? And what sites should we be looking at for the future? So the first thing we do is have a look at our projections. So Jason was part of the NARCLIM project, which was a New South Wales and ACT regional climate project, where he looked at using the weather research and forecasting model, which is one of the models that we use for our forecasting work. But they combined it with climate models and produced an ensemble. So an ensemble is essentially either a collection of different models where we have a look at the range of estimates that they can give us, or you run one model forward in time, but you change the initial parameters, and it gives you slightly different outcomes. So what he did was he had a look at the different emissions scenarios, and for 3 different time periods, for what we call the present, so we're going to call that roughly the last 20 years, the near future, which is a lot closer than we actually think, from 2020 to 2039, and then the far future. So in terms of our wind energy, we worked out what the extractable wind power was going to be across all of Australia. So we were looking at the amount of power that could be extracted from our wind turbines at an 80-metre hub height. So if we have a look here, and if we can think about where our wind farms are currently located, the last 20 years or so, we've got a huge concentration of wind around that South Australia region. We've got wind farms all around Victoria. We've got some amazing sites up in Western Australia. So where a lot of our wind farms have actually been located now are ideal sites as to what our model says, which is a really good indication. We can see there are a few locations in the red which show some really good extractable wind power potential. Now this comes back to Alistair answering his question, why would we maybe not want to put wind up in that location?
Whopping big cyclone.
Exactly. Thank you, Alistair. So if we have a look at our average annual number of tropical cyclones, we can see that from our red location up here, we may have a very good indication that we have high extractable wind power. But if we have a look at our cyclone paths, it may not be the best investment to be putting wind turbines in an area with extreme winds. So that's one of the things that we think about in terms of the location. It's not just what the data is telling us, it's also the weather that's associated with those locations as well. So you can't always just have a look at averages and say, well, this is what our data is telling us. Especially with technologies that rely a lot on the weather, you've got to really think about, well, what weather will those turbines, in this case, be experiencing? So then the next thing we did was we wanted to know, well, how is it going to change due to these emission scenarios and climate? So what we have here is the difference between what the present is saying is going to occur and what the near future and the far future are showing us. What I've circled or put in little boxes here, red is essentially wind farms where we know they actually exist, and the blue are sites that have been listed in different reports as potential locations for wind. And this will come in a little bit later as well. So we can see that in terms of the extractable wind power, we see a little bit of a decrease in the southern states. They're doing pretty well as it is, but due to climate change, we're going to see a bit of a decrease in what we can extract from those locations. We can see an increase in the far future, which is kind of interesting. So thinking about, well, does that mean we may be seeing more extreme weather and more cyclones occurring as we head out into the future? And then, of course, we were thinking about, well, from a research perspective, it's quite exciting having a look at these changes and also understanding what's happening. But in terms of what industry would be interested in and financiers and people like that, we thought the levelised cost of electricity was going to be a good metric to be able to put onto our maps to say, well, what's your investment going to look like now and what's your investment going to look like in the future? So what we have here is for our kind of recent past, our levelised cost of electricity map. So you can see we've included a lot of the energy transmission network. We have little dots that show locations of current wind farms in blue and the maroon are potential wind farms that we can see happening currently or in the future. So if we have a look at our map, we can see that, around the areas where most of our wind farms are actually located, we're getting around $100 to $125 per megawatt hour. It's a little bit higher, most probably, than what is being seen at the moment, but it's close enough in some areas, depending on the capacity factor of the wind farm, to give us a good idea of investment. So if we have a look at it in terms of the near future, how does that all change? Well, we can see that there's a whole big part of the middle of our continent where our cost has actually come down. Tasmania is always going to be an amazing wind resource because it lies along the Roaring Forties, and it's always just going to get better, and our figures actually show that. But if we drill down a little bit into kind of the specifics of it, if we have a look at a few existing wind farms that we chose in New South Wales, Victoria and South Australia, it shows us between the past, the near future and the far future, how our LCOE calculations change. And then the green one is what we're calling future. So if we take into account also technological advances in wind turbines, then how does that bring the cost down even more? So you can see, New South Wales, Victoria, South Australia, where we have quite a bit of wind and there's a good wind resource. It looks like continued investment in those areas is going to be beneficial. Again, Tasmania is always going to be an amazing place. So if there's land there, maybe you want to think about buying up now. You can sell it off to rent your land for a wind turbine. Queensland, though, is an interesting location. Having a look at a lot of studies, they talk about co-locating solar and wind in Queensland quite a bit, and there's a few ventures where they're doing that currently. And besides the threat of cyclones, if we have a look at some of these costs, they are quite on the high side. And even with advances in technology, it's not really coming down to a value that's, I think, worthwhile or economic. So in terms of what else is there for the future, there's a lot of people, I think, who are interested in solar. You all work in solar, or from the solar industry. So we're planning to do the same sort of thing for solar as well. We're also, I'm very interested in hybrid plants. So having a look at correlations and where is the best place to co-locate solar and wind. But that is a story for another day. So I'd just like to say thank you for listening to me talk about my research. And